So today we have a busy schedule, but I promised to make a break. One of the students told me that without a break it's not human. So okay, there will be a break. Again, a heavy schedule. I want to finish telling you some things about Dzerzhinsky, and then go to the part which is closer to my personal interest, but with some general background, of course, which is exactly solvable systems and exact solutions, and so on. So if you remember last time, I showed you how Dzerzhinsky obtained his identity in his very original first paper by using Hamiltonian dynamics. So the system is prepared at thermal equilibrium. The initial condition is sampled according to Gibbs, Maxwell, Boltzmann measure, exponential minus beta E over z. And then the environment is unplugged. The system evolves in a Hamiltonian way. And after a finite time, your protocol ends and the heat bath is replugged and the system converges towards another thermal equilibrium. And the proof of this identity in the Hamiltonian case is quite easy. If you remember, the basic point was just conservation of phase space volume, Liouville theorem, and a very simple simplification because the work was in fact a perfect derivative. So in fact you got exponential minus hb plus ha times exponential minus ha, things simplified, and you got the integral of exponential minus the final Hamiltonian, which is the final free energy, if you want, or z. Okay, just don't do it again. But of course, as I told you, it's not very nice to unplug the environment. We want to have a mechanical description somehow of the heat exchanges with the bath. And as I said, I think the Dzerzhinsky identity has been proved in 15 or more different setups. So there are many proofs. And more importantly, it has been really assessed in the experimental lab. So now people really believe in it. But I think it would be pedagogically nice to give you another proof, which is in the Langevin case, especially, of course, not for the grown-ups, but for the students. It's a nice way of using path integrals. So it will be a nice exercise with path integrals to prove Dzerzhinsky in the Langevin setup. So let's take a Langevin equation. So we represent the thermal interactions through a noise, through a thermal noise. And the most general setup would be just, extending the Hamilton equations by adding dissipation and noise related by fluctuation dissipation theorem. So I have some external potential, okay, which depends on some protocol, which can be time dependent, and I put on some noise and some dissipation. And the noise is Gaussian. Let's say white for the moment. If I remember, I will tell you something about non-white noise, but let's take it white. And of course, because of fluctuation dissipation theorem, we have to put gamma here, the same gamma which is here, okay? So that we have reversibility, at least if it's time independent. Okay, so this would be the most general setup with a Hamiltonian, which would be in fact half p square over m plus a potential, which depends on time through some parameter, through some protocol. Okay, I'm writing everything in one dimension, but you can put arrows and have vectors if you want, which doesn't make a lot of difference. Okay, and the work is defined as lambda dot dh over d lambda, but h depends only on lambda through u, so it's really du d lambda of x of t dt. So that's the whole setup. And what we want to prove is that the exponential of minus the work over kt is equal to exponential minus beta delta f, Dzerzhinsky identity. Okay, this is possible to do it in this setup. I want to simplify things further because I don't want to write longer equations. I want to do the overdamped case. which means that I'm taking mass equal to 0 formally. I want to go back to a first order differential equation. So as you know, when mass goes to 0, the p terms go away and so on, and we end up with a simpler Langevin equation. I also take, by rescaling time, I don't want to carry on gammas everywhere. You can put them back if you want, but I take gamma equal to 1 by rescaling time. Of course, dimensionally it's less nice, but I will have less things to write on the blackboard. So the equation becomes like that. And I want to prove Jarzynski for such a stochastic differential equation with a potential which depends on some protocol lambda. And the thing is that at t equal to 0, I take an initial condition. Any question? No. Because I rescale time and I'm lazy, I don't want to carry on.
1 or 0?
Gamma is 1. 1. I take the overdamped case, and I don't want to carry one more symbol to write on the blackboard during half an hour. But you can put it back just by dimensional analysis. It will be 1 over gamma here, 1 over gamma here, and so on and so on. So the initial condition you sample with Gibbs measure. So you take exponential minus 1 over kt, which I will write as beta soon, u of the original over ZA. So again, if you remember, at t equal to 0, lambda of time starts from some lambda a, which I call a, and at the final time, it goes to some value b, and in between it does whatever it wants, and then it stays at b. Okay, so now I want to prove Jarzynski. I will give you some examples and exercise. So one exercise you could do, which is a very good exercise to understand how things work. There's one case which is solvable, is when the u is parabolic, quadratic. Then you get a linear Langevin equation. You can do everything. Okay. So exercise, if u is half, what can we take as example? I think I wrote this just to set up the notation so that you don't have to invent them yourself. We take a parabola. This is the usual thing in which the middle, the center is being shifted. Experimentalists love that. Something like that. Then you see you will end up with a linear Langevin equation. Everything can be computed by hand. You can compute the work, and you can prove Jarzynski. It's not totally trivial, but you can prove it by just brute force calculations. Okay? So you can prove Jarzynski in this case. It's a good exercise because there's a kind of beautiful cancellation in your calculations, and it seems like magic, you know. Okay, but we are going to prove it for any u. So for any u, we cannot solve this equation. It's nonlinear and stochastic. So we have to do something else, and we have to go through path integrals. So we have to use path integrals. So I will do a crash course on path integrals for maybe some students who may not have used them so often. So remember that if I have a single Gaussian variable, Gaussian, which I call psi, the probability distribution of psi is exponential minus psi square, 2 sigma square, 2 pi sigma square. That's a single Gaussian variable. Okay. What is a white noise? If you discretize that, it's a series of Gaussian variables sampled every time delta t, and with a variance which is of the order of 1 over delta t, because the delta function goes up to delta t. Yeah, 1 over delta t. Okay, so in fact, what I have for a white noise, so again, sorry for the aficionados. Of course, most of the people know that absolutely perfectly. But between time 0 and Tf, I make small intervals of size delta t. Okay, and now the probability distribution of my noise, if I discretize my noise, I forget that I'm doing some continuous thing. So the total number of intervals is t over delta t. The f here will be forgotten very soon because it's a bit long. Okay, to write. And the distribution of this process is the distribution of the noise on the first interval, the second interval, the nth interval, and they are Gaussian variables which are independent from each other. Okay? So the only thing we have to know is their correlations. Well, we just have to discretize this identity and this definition, and it will become, I replace my Dirac delta by a Kronecker delta. So gamma is 1 now, because I don't want to write it. And the discretized version of my process is just this. So now I just have a bunch of independent Gaussian random variables every interval delta t, and they are totally independent, and the variance of one of them, I equal to j, is of the order 1 over delta t. Okay. So now I can do all the statistics. I know, just by using that n times, and plugging sigma by that. So if I do things a bit carefully, up to a normalization, my distribution would be the following. Psi I square, I equal to 1 to n, and 4 kBt, because there's a 2 sigma and there's a 2 here, and the delta t comes in front. So of course, if we go to the continuous limit, this thing becomes a Riemann. I hope there's no mathematician anymore. It becomes a Riemann integral, and I'm tired of writing 1 over kBt, so I will call it beta as usual, of course. Beta over 4 integral sum from 0 to the final time dt psi of t squared. And this is the continuous measure of my process. Okay, so we are almost done, at least for the preliminaries. What is a stochastic differential equation? A stochastic differential equation is a change of variables. I go from Gaussian white noise, and my equation is a black box, a transfer, not matrix, it's not linear, but a nonlinear transfer operator, which takes the Gaussian measure from psi and puts it into x. Just like when I had one variable here, if I have some x, which is a function of psi, well, I have this good old equation, the distribution of x, px dx, is given by p psi d psi. The mistake we all make when we are kids is to forget the dx and the d psi, so we cannot just substitute, but okay. So here, this differential equation is just a way, if you discretize it, of transferring the psi1, psi-n into x1, xn with the knowledge of x0, which is sampled with this Boltzmann distribution. So we'll make a change of variables and write the measure for x. So this is what I'm going to be super slopey. So sorry for, again, the professionals. Well, I'll do it and then try to justify. So this is the change of variables, finally. I just rewrite my equation the other way around. So I know the distribution of these guys. It's given here. I just have to substitute this quantity. Okay, I'm being a bit sloppy, because I forgot the Jacobian. There is a Jacobian of the change of variables. So forgive me, but I'm not going to write it. Okay? You can, because it will just take a little time to go into Ito Stratonovich, and if I just write it, it will just go through the whole derivation. So I'm not cheating completely. I'm just not writing a term which is completely transparent. Or maybe I write it in the first equation, and then I will just forget about it. By the way, if you use the so-called Ito discretization, because I'm discretizing everything, so I have to discretize this equation, the Jacobian is 1. So in this case, I'm not even cheating. Well, almost not. Okay, so I can just write the distribution of my x. So what is the probability that my process x of t, my particle, my Brownian particle, ends up at xf, knowing that at time 0, it was at xt0, x0, and I think I will need a bigger board than that. Can you read when I'm writing here? No? You can, yeah. But no. So, well, you'll have to buy another board. Okay, so I will start again here. I will write my measure here. You know the setup anyway. So the idea is that you just substitute this thing into here to get the measure. And again, I'm throwing the Jacobian away because I don't want to be carrying it just for sake of rigor. But if you do, the proof remains true, of course. So the probability of, I erase the equation, which is a bad idea. X dot is minus du lambda dx plus white noise. And the distribution of the path probabilities ending at time tf at xf, knowing that at time 0 I was at x0, is just the integral over all possible paths, trajectories, between time 0 and tf, which started at 0, x0, and ended at tf at xf, of this measure. Exponential minus beta over 4, integral from 0 to tf, dt, x dot t, plus du lambda over dx squared. And this depends on x of t. Maybe I should write it at least once. This depends on x of t. I will stop writing all the arguments very soon. Squared. And as I told you, there is a Jacobian, which is the change of variable from xi to x or x to xi. And I'm going to not to write it, because if I write it, it will just go through till the end. Is it okay? This is the measure of one path, and I'm integrating over all possible paths, which starts from the point I like, x0, and end up at the point I want to end up. And because of stochasticity, there is no more unicity, so there can be plenty of paths doing that. Okay. Now, maybe I should take some colors, because we'll have to transform all that. So I have the advantage over you that I can use the blackboard and erase things. I'm interested in computing the average of the work, the exponential of the work. This is what I'm interested in. I have the probability measure, so I'm just going to wrap up things together. So what is that? I take this. So all possible paths which end up anywhere. Remember that I sample the initial condition with respect to Gibbs measure. Okay? And now I have to integrate over all possible paths. So I just write again this object, path integral, exponential minus beta over 4. So now I'm going to write less details. I just write x dot plus du lambda over dx squared. And the thing I want to average, I have to put it inside too. So the thing I want to average is exponential minus beta of the work. And if you remember, the definition of the Dzerzhinsky work was lambda dot of t du lambda over dt, d lambda x of t dt. Okay, I have everything now together on the blackboard. Here?
Yes,
I'm sampling it. Okay, you want me to write it here? You're right. Thank you. Yeah, and then, okay, this is here also. Yes, of course. Thank you.
What does the index capital A stand for?
This is the initial value of my lambda 0, which I call A. I say that my protocol, lambda of time, lambda, because I don't want to carry two indices, lambda 0, I call it A. So it starts at a value A, it does anything it likes up to time Tf, and then ends up at value B. Initial volume, final volume. Okay, so now we are done. Maybe I should have some color pens, but because it's very visual, in fact, totally visual, I will use a very nice identity that we all know. A plus b square is a minus b square plus 4ab. Okay? So, the idea is the following. I will change the sign here. Yeah? So I put a minus here. Maybe in black. X dot minus du d lambda x squared plus 4ab x dot du d lambda. Are you with me? Okay. What I'm doing, because it's a square, I can put the minus here. I'm reversing time, what I'm doing here. Okay. Now this 4 here will kill the 4 here. And this part, x dot du d lambda dx, with the right sign, will merge with lambda dot du d lambda. Okay, I'll do it slowly. So, so I can put the 1 over ZA outside. The only thing is not to forget some of the terms, but otherwise it's very easy. dx0, dxf, exponential minus ua, beta ua of x0, thanks to Arnab, and ZA is already outside. And what I have here is exponential minus beta. So I will group these two terms and this one with the integral and the minus beta over 4, and this will give me a complete derivative of u. The integral of x dot du dx plus lambda dot du d lambda. Okay? Yeah? And my path integral measure with a minus sign. Minus beta over 4 integral of minus x dot plus du dx. And of course, I'm sorry, but you will have to complete and put the indices lambda and everything where they are. Is it okay? The pattern is okay? Okay, so now I'm almost done. I'm sorry?
No, X dot.
Here?
No,
Oh.
The first one, X looks like I.
Oh, sorry. I'm just taking this term. I forgot something else. D. Sum of.
Capital D.
Oh, this one, the path integral. Sorry, I don't have any room to write it, but the integral is there. It's okay. It's here. Okay. So I should need a bigger one. Okay. Is it okay? Okay. So now you can almost complete it by yourself. This is an exact derivative. You know, just like in the proof for the Hamiltonian case. This is a total derivative with respect to time. And we are integrating over dt, of course. So this is just du lambda dt times dt. So it's u of lambda final minus u of lambda initial, ub minus ua. So this term gives me exponential minus beta ub of x final minus ua of x0. Okay? Yeah? This guy will kill this guy, like before. So this guy cancels with this one. Okay? This one, because when I have a path integral, don't forget that I'm integrating with fixed boundaries, which I never wrote again, but I should write them. So x0 is equal to x0, x at time final is equal to x final. So I can bring this out because this is fixed. So this thing becomes integral 1 minus ZA dxf exponential minus beta ub of xf dx0. Now this thing has been killed. The ZA is just a constant which is outside. Okay, and my path integral dxt x0 is equal to x0, x final is equal to x final, and this object minus beta over 4 integral of minus x dot plus du dx squared. And this Jacobian, which I never wrote, which we'll just go through. Okay, are you still with me? Okay, so now we just have to do that. So we are almost done. Just have to be a bit careful. Well, this thing we know how to compute, in fact. So this is easy. We just have to look at this. You see, if we didn't have the minus here, it would be just a path integral. So we want to get rid of the minus here. So don't forget that what we have here is the continuous limit of a trajectory. So you remember x1t, x2t, and xn, if I cut my trajectories into n different small pieces. So I will make a change of variable just by reverting time. I will call x hat of t is x of t final minus t initial, minus t. You know, I have n variable, x1, x2, xn, and I have an nth-fold integral. I just swap them. I call xn x1, x2, xn minus 1, and so on. The Jacobian is 1. It's just a change of numeration of my variable. So what will happen, and I will just use my blackboard, this will become a hat if I make this change of variable. But of course the sign here will be changed because the time derivative will become the opposite. Again, I have an n-fold integral and I'm just reverting the numbers, the names. And of course, initial and final condition will be swept. So now I'm starting x hat with TF, xf, and x hat of the final time is x0. Yes? So now how do you interpret that? If you look at it, what we are computing here is the path integral with this quantity here. Well, what do I want to show? What do you think this quantity is equal to? It should be 1. Why? Because what is this? This represents the probability for the trajectory x hat to start at any point xf fixed and to end up anywhere, but I'm integrating over the possible ends. So the x hat, now if I forget about everything I did before, what does this represent? This represents the sum over all integrals of trajectories, hats, okay, starting at xf and ending anywhere. They can end anywhere, but they start at xf. Well, if they can end anywhere, this is just the probability of going from somewhere to anywhere else. So this is 1. Yeah? Is it okay? This is 1. Oh, yeah, but x hat and x, I can just change it. Yeah. It's a function of x, but you're right. If I was very, very, very careful, I should also change x hat here and change and reverse my protocol. But I don't really care. I just have now a stochastic partial differential equation for x hat with u lambda hat, which just, starts from xf and goes anywhere. So this is 1. This is the same as conservation of volume. It plays the same role in this context. Well, okay, this is 1, so this thing goes away, and this is just zf. So I end up with zb over za. This is just the z, and this is exactly Dzerzhinsky identity, because this is exponential minus beta fb minus fa. So the only slightly subtle point is here, but once you recognize what this thing represents, it represents of a Brownian motion, if you want, with some potential that starts somewhere, and you're adding up about on the end points. So it's 1. Okay.
Normalization of this probability, the Jacobian that you
yes,
use,
so the whole Jacobian will come here, and in fact, it's really the whole thing which represents 1. If I take Ito, it's 1. So I can always, escape by saying that I'm taking the Ito convention, which personally I don't like so much. I prefer the Stratonovich. So the Jacobian, just for the aficionados, the Jacobian, which I never wrote, would be 1 for the Ito convention, and it would be 1/2, maybe minus, second derivative of u, but which is even, in fact, and it will be harmless. Okay? So if you want to do things very cleanly, indeed you should put the Jacobian and check that, of course, it does not have a sign or anything, and it works. Okay, so we have now the proof of Dzerzhinsky, and we can make some comments. First of all, you remember, so I give you that as exercises or examples as you prefer. You remember that I did the overdamped case? So you can first exercise, extend the proof in the general Hamilton, without overdamping, for non-zero mass, for the second order equation that I wrote in the beginning. This can be done. You have to be a bit careful about writing now double path integrals according to position and velocity with the constraint that the time derivative of the position is the velocity, but it works. It's just messy. Okay, another thing you can show, and this is, again, you do it in the overdamped case, and this will be, again, harmless. Here I computed this thing, but I could have added, as I did last week, fugacity parameter. I could have computed, instead of that, I could have computed for an arbitrary gamma this object, where gamma is an arbitrary parameter, a Laplace parameter. If you just think about a second, it will just go through. Yeah, some signs will change because the work is an integral and I'm changing t into minus t. But if you do the exercise, and this is a good exercise, you will end up with this identity for any gamma. And of course, Dzerzhinsky identity is a special case for gamma equal to 0. Is exponential minus beta delta f. Can you read? Probably not anymore. Times exponential gamma w for any gamma. This is just a very, very simple extension of what we did. Okay? But here there's a minus, but no here. If I'm not mistaken, no. There's no minus here. Because we reverted some things, and if you do it carefully, you will see that, you have to do it again, and you will see that there's no minus here. Okay, so this tells you something about the probability distribution, because whenever you put a gamma here, you're doing Laplace transforms. So you know something about the probability distribution of the work. So what we proved here is Crookes identity, which I will write now in a more familiar way. What we have. So I will erase that. Is there any question about this derivation? No, it's okay? I think it's by the way, I didn't use path integrals just to be fancy. If you really think about it, there's no other possible proof for arbitrary potential. There's no other way of doing it. No, I don't think so, because in fact gamma goes to minus beta. This gives you 1. Yeah, but then you will do Dzerzhinsky backwards, and this will cancel this guy, and this will give you 1. So it's really a plus. Yeah. If you put gamma equal to 0, you have Dzerzhinsky. And if you put gamma equal to minus beta, you have Dzerzhinsky. But I was a bit sloppy here. It's for the reverse process, which means that you're exchanging delta f into minus delta f. But I was going to talk about it. So it's really plus gamma. Again, I'm going fast on purpose because if you're just looking at, I understand. I go often to lectures and I never read my notes again and never do the exercises. But you can always hope there is one person who just, or one half person who does through, and then you learn. Anyway, so the Crookes identity, which is in fact here in Laplace transform, but the way it's written in more palatable way, is a property of distributions. So it's just the inverse Laplace transform of this thing. And the Crookes identity tells you that if you have a protocol going from A to B, if you look at the distribution of the work forward, so you have a protocol lambda, then you look at the distribution of minus the work, which is the minus gamma there, but reversing the protocol, exponential beta w minus delta f. So the idea is that you take your RNA, or whatever, you do some protocol on it, and you measure not only the average of exponential minus beta w, but you're really able, and Bustamante did it, to monitor and to get the distribution of the work. Suppose you can do that. You do your experiments plenty of times, and you get the distribution of the work. Now you can do your protocol in a reverse manner and get the distribution of the reversed work in the reverse protocol, and I should draw it nice. And this is the other distribution. Okay, I plot the distribution of minus, the same thing almost, for the reverse protocol. So what Dzerzhinsky tells you is that, in fact, these two functions are related with this identity. So if you know one, you know the other one. So you don't need to know both of them. And look at when omega is equal to delta f, the ratio is 1, so they cross at delta f. So in some ideal experiment, which in fact not ideal, Bustamante did it with other people, Tinoco, Lippard, Dzerzhinsky himself, of pulling on RNA strands and denaturing them and then closing them back. They were really able to measure points on these distributions, forward and backward, and they were really able to show that they cross on delta f and that they have this relation, the experimental points. So if you know one, you know the other one. Well, I even have the reference. So Tinoco Lippard is the first author. Many people, Bustamante. So this is experimental. Huh? Nature. (437), and this was in 2005, already quite a long time ago. And there have been many experimental other checks, for example, in the group of Siliberto at ENS Nyon. They use rather mechanical devices, Sergio Siliberto et al. In the same years, and they continue working on that and on information theory, and probably many others now. Okay. Again, we could spend 4 hours on Dzerzhinsky. This is, of course, worth it, and there are many, many things to say, but I would like to go on. Another Dzerzhinsky's papers are very, very beautifully written. He writes very, very well. They are deep and extremely well written. There are many of them. You can choose any one. But for example, he wrote a very nice review, probably for a StatPhys meeting. And there are some more recent ones too, in some books. But for example, this one contains a lot of Europhysics letters, a lot of references, and a lot of explanations. No, not letters. Sorry, Europhysics Journal B. '64, page 331. And this was in 10 years ago. But there are some more recent ones where new things are being added. But just Google him and. By the way, the path integral thing, well, in fact, quite a few people discovered it simultaneously. There was a paper of Dzerzhinsky and collaborators, Cherkov and others, almost 10 years ago. There's a nice paper by Attila Szabo that probably many of you know. Who proved this using the same method. And in fact, we were quite unfortunate. My friend and colleague, Henri Orland, whom you know very well, suggested that we should look at these kind of things 10 years ago. So we got excited, we wrote notes and so on, and found this derivation by path integrals. Then we realized that just 1 year before, Dzerzhinsky had written a paper with Cherkov with the same technique. But anyway, it's a good exercise in path integrals. Another example and exercise I want to give you, because again, Dzerzhinsky's identity looks both simple and counterintuitive, is the example which was treated by Lua and Grossberg. So again, people from soft condensed matter theory. And according to what Grossberg told us when he visited us in Saclay a few years ago, he wanted to disprove Dzerzhinsky identity on an example, and ended up giving a beautiful exact calculation that proves it. And this is the following exercise. By the way, maybe we should not record it, but it can be a very good exercise for a problem for students. You can make a good exam from it. I'm thinking about it. I hope they will not look at this video. You take the basic piston and gas thing, and you take a single particle, a perfect gas with a single particle in one dimension. So this guy is bouncing and bouncing back, and so this is a Maxwell particle distributed according to Maxwell's law, beta mv square, okay, normalization, and you pull over the piston with any prescribed speed, and you double the volume of your thing in a given time. And then it's really mechanics. You just count the bouncing forth and back, and how many bouncing there will be in a given time that you need to reach the double volume. And each time the particle bounces, so suppose that the particle comes with a speed v, small v, which has to be bigger than capital V anyway, well, then it goes back with 2v minus small v, just, mechanics. So you can compute how much work you did on your particle. It's just Federer playing tennis with a ball. Okay, and then you compute how much work you do, and you average it over the Maxwell distribution and the number of bounces, because if the particle is super fast, then it may bounce many times. This is rare, but it may happen. And once you finish the calculation, which is again a perfect exercise in StatMech 1, if you want, you show that Dzerzhinsky identity is true. So this goes back to a question I had at my colloquium, but unfortunately I think the person is not there anymore, but you'll tell him. You remember this paradox, if I have one, if it's a perfect gas, it doesn't make a difference if I have many. It's just, adding up things. If I have a perfect gas on your half box, and you make the separation disappear, you make no work. We learned that from the very Joule. This is called Joule expansion in thermodynamics books. No work, no heat. So no variation of energy according to the first principle. Only the entropy, the volume has doubled. So the entropy has been multiplied by n log 2. Yes. So exponential minus delta f times beta is equal to 2 to the power n, if you do things carefully. And you would say there is no work. So Dzerzhinsky is wrong, because exponential minus beta w is 1. Yeah? I don't perform any work. That's what we learn in thermodynamics when we are kids. Some of you are still kids. Okay, but no work, so there's no way that this can be true. Because this would be 1, and this would be 2 to the power n. But of course it's not true. Dzerzhinsky is right. I didn't really tell you. I mean, it's not a miracle. The wall did not vanish like that. So one has to specify what you do exactly to remove the wall. So what you do exactly to remove the wall is, for example, you pull it to the right hand very, very fast. But then, according to Maxwell distribution, or if you prefer Lua and Grossberg's calculation, even if you pull your wall, this separation very fast to the right, there will be always some Maxwell particles which go faster and bounce over it. if you even really think about them and go back to Federer, the ones which will receive the biggest amount of work are those coming with speed 2v and which are just stopped by your racket, by your wall. These ones will get a huge amount of work. And if you just trace that, they are of course extremely rare because they have a huge speed, but they get a huge amount of work. And exactly the one you need to compensate. This is a very, very, very small number, and this is exactly the inverse number. And multiplying them and making statistics gives you that. So this you can try to do. Yeah?
What about sliding the wall after?
This is a very good question, and I didn't want to answer that one. This is, forget about it. So there are a few, this is a very good question, of course. Two things. It's a non-Hamiltonian thing. So I cannot really represent it cleanly as a Hamiltonian. There's another way of saying it, and this is more clean, and this was done, in fact, quite recently by Dzerzhinsky with an Indian postdoc or PhD student, and because he's a South Indian, I don't remember the name. It's a long name. I only remember short names from North India, like mine. Anyway, it's a Venkata Raman, Raja Raman, and so on, something like that. Sorry for him. It should not be filmed. The thing is that there is a kind of extended, here when you do like that, you're really modifying the phase space of your system. You're changing the phase space. So in fact, there is a modified Dzerzhinsky identity where you should put a factor of contraction of phase space. And if you do it cleanly, even this case is saved.
In what sense you modify the phase space?
Well, somehow, again, it's not a Hamiltonian thing where you're moving this wall, so you cannot represent it as a force on the wall. You're really changing the space of configurations.
Yeah, I think one can do it a little bit more cleanly without changing phase space. Instead of having some mathematical wall, just have wall of finite thickness, which you are moving out.
Yeah.
And then work actually perform.
This is the next exercise. This is the next exercise.
Yeah.
So next exercise, I didn't want to talk about it because, well, I think you will have no pause. Sorry. No, I'm joking. So this is exactly the next thing. How do you remove the wall? Another way of removing the wall is to saying that I have a potential. So that's the half of the wall. There's a full wall. I have a potential here which is 0. And I have a very, very, very high potential here, for example. Super high potential. And removing the wall, which means that I'm very unlikely to be here. Removing the wall means to bring down this potential. Do the calculation. That's an even, you cannot give it as an exam. It's too easy. The calculations are in the notes if you want to look at them. I really don't want to do it now because I'm getting out of time. But it's a very simple calculation of comparing the stat phase of these two processes, and Dzerzhinsky will be saved. So it works. Okay, I don't wanted to say something before the pause. It's good because we're arriving at 1 hour. I wanted to say a few things. So first of all, but very, very rapidly, again, this would deserve hours. I didn't talk at all about the quantum case. Quantum Dzerzhinsky exists. It's a bit complicated. So why is it complicated? Let's go back to the Hamiltonian proof. I just want to sketch again to show you the difficulties. If you remember, we were integrating over phase space, dx dp, some exponential minus beta ha of x0, so this was x final, p final, and the work was over ZA, and the work was a perfect integral. So we wrote it like that. You remember that, I just said it again today while starting. But we used uv in the end. Or what I'm calling z is, of course, the phase space variable. Well, you will see immediately what happens in the quantum case, which makes things difficult. So what we said is that this thing kills this one. Okay? So this is classical. First of all, in the quantum case, we have to replace this integral by a trace over the density matrix. And this will be the density matrix, the Gibson density matrix. Then, well, here we make things commute. Okay. In quantum mechanics, if I put operators here, I'm stuck. Exponential minus beta HB minus HA is not the product of the exponentials. They don't commute anymore. So you're stuck. Okay? So it's already one difficulty. So you have to change the definition of the work. You have to define the exponential of the work to be, which is a kind of operator, not exactly, but to be something like that, so that it cancels. And so on and so on. So things become more contrived in quantum mechanics. It is possible. Many people worked on that, including Dzerzhinsky himself, Korshan, the Japanese school, I had other names. Shaul Mukamel also, the brother of David Mukamel, wrote with Esposito quite a few important papers on this subject. And there are quite a few papers, but you see that the difficulty is there. Non-commutativity. Another difficulty is defining the work. The work is the force times the distance. There's no force in quantum mechanics, so you have to twist things a bit. So somehow the Hamiltonian proof can be saved. If you want to have a kind of Markovian proof, quantum Markovian proof, you have to go to these Lindblad operators. Again, I'm just throwing words, but keywords. And this was investigated, for example, by Crookes, the same Crookes, and in fact also by Chetrit and myself. We wrote a paper a few years ago, almost 10 years ago, Raphael Chetrit, where we found an equivalent of Dzerzhinsky identity, but in the quantum case. It was 6 years ago. But it's quite complicated. It's not completely satisfactory, and in fact I'm still working on it. I'm still trying to find some semi-classical limit which would be more intuitive. This can be also extended to field theory. You can take fields. You don't need to take only x dot. You can take a model A or model B. So Dzerzhinsky is still true for field theory. For example, model A, if you know what it is. Okay, so it's still true, and the same path integral proof works. And in fact, if you like field theory, I don't know if there are any high energy physicists among us, but probably not. In case of field theory, you can show that Dzerzhinsky comes from some symmetry of the action. In fact, Dzerzhinsky is related to a supersymmetry of the action. Supersymmetry of the action. So as you know, in field theory, when you have some symmetry of your action, you have some identities which come for free. They are called Ward identities. Well, in fact, Dzerzhinsky is a kind of Ward identity for a supersymmetric invariance of the action. So this is something we did with Moshe from Technion and Henri Orlan. So finally, we were able to publish something in a wider context. And this was maybe 10 years ago. Again, I'm not really trying to sell my things, but you can find, I know what I did, you know. I think Michael told me yesterday that when you're young, you remember other people's papers. When you get older, you remember your own, and I think I'm on the threshold of not even remembering my own, so. But at least I know there are good references there. We were careful to write references, and this one has huge amount of references. Raphael Chetrit is very careful about references, so maybe there are hundreds of references, and if you want to learn more, you can always pick up the references from these papers. Okay, I think this is the time for stopping. I will, maybe last word. I wanted, but I will not, because it's too long. This Dzerzhinsky is a kind of, you know it's important. It has been a seed which has bloomed, and many people are now exploring that. It is the beginning of a story that people call stochastic thermodynamics, with many extensions and so on, which is the idea that Langevin equations or Markov equations, you can define for them entropies, free energies, Dzerzhinsky identities. There are many, many people who are very active in that field. And especially I recommend you, if you are interested in stochastic thermodynamics, I never really worked on that, so I'm not really an expert, but there's a very, very nice review by Udo Seifert, which is called Stochastic Thermodynamics. Seifert, who's one of the major players in this game. Seifert was able to define cleanly what is meant by the entropy production of a single trajectory. And then the total entropy production by a system will be viewed as an average over path integrals over each trajectory of this single entropy production. So there is a nice review by Seifert, and you may consult it if you want to know more about stochastic thermodynamics. So it's a good time to make a pause, and then we shall embark to a new chapter about exactly solvable models, exact solutions, and the other point of view. Any question? So how long the pause? 2 minutes? 3 or 2.5 lectures were about this strategy from going to above to down, which means that I tried to explain to you some general theorems or general identities, like Garavoti-Cohen, generalized detailed balance, Dzerzhinsky. So, like thermodynamics, things which are true under some very mild hypotheses and should apply to many, if not all, systems, and you get, identities. Then if in any precise system, they should be true. But the other strategy is rather going from down to up. So this is exactly solvable models. The idea is to try to beat up some simple models which have some special features. They can be computed, you can do things with them, they are solvable, and then you learn from this experience you have from specific models. You try to generalize, you try to say, okay, the properties I found in some model, I can, generalize it, or you see some features, some phenomenon. So of course this was very much done in statistical physics at equilibrium to learn phase transition, solving Onsager's solution or Peierls' analysis of the 2D Ising model was extremely important. Peierls proved the existence, mathematical existence of phase transitions on the 2D Ising by this very nice, calculation of contour, classical things, and this was very useful. Of course, you have vertex models, ice-type models. There is a book by Baxter in which you have hundreds of different models which have been solved using more and more sophisticated techniques. And for example, investigating critical exponents was very important to know about models and find relations. Similarly, in quantum physics, you have spin chains, Heisenberg spin chains, Hubbard model, which is not exactly solvable, but you can learn things from looking at models. So you remember about the ideal picture I've been drawing for now 2 weeks. Don't worry, I'm flying back in a few days, so I'm not going to bore you with that forever. But this, okay, 2 reservoirs with particles flowing or heat flowing from left to right. Well, if I can try to sell it, one way of representing this as a very simple model is through the so-called asymmetric simple exclusion process. And this is one of the simplest models you can think about. You have a finite lattice with L sides, particles, random walkers hopping on it. and particles which can enter from the left reservoir or exit, or enter or exit from the right reservoir. So now that we have talked about Markov processes, let's be slightly more precise. So it's a continuous time Markov process. A particle can jump asymmetrically between time t and t plus dt. It has a probability p dt to jump to the right, the next side to the right. So it's p is the rate. It can jump with a priori a different probability rate q to the left. Particles can enter, if the site 1, let's say, is empty, can enter with rate alpha, exit with rate gamma, and from the right, well, I think I made a mistake. Usually we call this one delta, but it's not so important. Okay, this would be, of course, trivial if we don't add an interaction between particles. So we add hardcore interaction. Double occupancy is forbidden. These are not fermions, but it's a kind of exclusion principle at the classical level. So this is the exclusion hardcore interaction. So now you have a real interacting particle system, okay, with open boundaries and with some dynamics. And the rules are totally specified. And this model looks a bit naive, even stupid, but it's, in fact, it's a good model. And, not completely obvious from the beginning it's a good model, but at least you can say that there has been thousands of papers on this model in the last 25, 30 years, at least. And this is a minimal model. It's a model which is rich enough to capture some physics, okay, and simple enough to be computable. You can do things with it. It's not, if you start adding more features, it becomes more interesting, but you cannot do exact calculations anymore. So it's just on this very special line. So again, many things we could say about this model. It breaks detailed balance if P is different from Q, or if the boundary rates are not adjusted in a very, very special manner. The two fugacities of the two reservoirs will be different. So detailed balance is broken both in the bulk, if P is different from Q, and from the boundaries. So it's out of equilibrium. There is no Hamiltonian. It's a Markov system, so no energy, no way of writing any Boltzmann weights. And because of the interactions, it's a true n-body problem. It's non-trivial. So because it's minimal, it appeared in many, many different contexts, because many people discovered it simultaneously, starting from 1968, where it was found or invented by Caroline MacDonald, Gibbs, and I'm not going to make the same stupid joke again, and Pipkin, who are biophysicists and who wanted to see how ribosomes translate messenger RNA through these enzymes which build proteins. So they are kind of, machinery at the molecular level, and these, call them motors or enzymes, they proceed along the strand, but they cannot overtake each other. So of course they are 3 sides long, which is already too complicated for a mathematical physicist. We go back to 1 here, but the main features of the exclusion process were already there. I'll just give you a rapid list of different places where this thing was invented in the 70s. People in solid-state physics studied hopping conductivity with holes, so they used a kind of exclusion process. Of course, transport of macromolecules in very thin capillary vessels, so there was a community working on that. There's a very classical paper of Alexander and Pincus, I think early 80s probably, half-page paper, but very deep. But there were other people working on that too. Reptation models. There are papers by Ben Widom and Jean-Louis Viovi in the 80s who used an exclusion process. Again, you have to dress it with more features to represent repetition, directed polymers in random media, traffic. People played with these models. Again, you have to add features, but this is a minimal model for traffic flow. Interface dynamics, this I'm going to talk a lot about it, and KPZ equation. So it's, again, a minimal model. It's just on the right boundary between being tractable and being non-trivial. So it's a good model. And in non-equilibrium physics, it was really, it came in the 80s, I think 84, you'll have to check the date, by Katz, Leibowitz, and Spohn. There's a seminal paper, probably in GStat Phys, about driven lattice gases, where they considered DDRs, driven lattice gases, in which they invented plenty of models of non-equilibrium systems. And again, the exclusion process is a special case, but it's a kind of distinguished special case in this whole class. You can define it in higher dimensions. It's less interesting, becomes somehow trivial, and becomes untractable analytically in higher dimensions. And it's also in queuing process and so on. Driven diffusive systems, DDS. Probably this was the right title. The right title was. All this you can find easily on Google. So another thing which is interesting with this model is that you can map it to plenty of known models. So, okay, I have a whole list of choice, but for example, you can show that this asymmetric exclusion process, ASAP, is equivalent to a spin chain, a quantum spin chain, a Heisenberg spin chain, but in an imaginary time. So maybe this way we'll spend a few minutes to show you the mapping, because it's important. So why? Well, because if you remember, on the Markov side of the process, we are writing a Markov equation, a master equation. This was the very first lecture 1 week ago. The only thing we can write about the system is the Markov equation. So everything is embedded in this Markov matrix. I can write it as a vector. P dot is MP. And if I can solve formally this equation, of course. P of t is exponential mt times p at t equal to 0. The point that to be able to compute that, I should be able to diagonalize my matrix M and find the eigenvectors to compute that. But in fact, when we solve a Schrödinger equation, we do something like that in imaginary time with a Hamiltonian. So it's already a good indication that in fact this model should have some relation with some quantum thing. So by the way, if I look at what's happening here in the bulk, I am going to be sloppy about the boundary things, the boundary conditions. I will come back to it next week, next lecture, last lecture, where boundary condition will play an important role. But if I look at what's happening in the bulk for my matrix, so I'm between site I and I plus 1. So this bond can have 4 states, empty, 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 occupied, occupied, empty, occupied, occupied. So this bond, the local update operator, the local Markov matrix in this basis. So I hope you understand what I mean. The 2 sides are empty. Here, first one is empty, the next one is occupied, and so on. If you look at what it can do, well, if the 2 bonds are empty, and I forgot about what's happening before. I'm just writing a local operator here, where nothing can happen. I'm not thinking about I plus 1 and I plus 2. Just update of this bond internal. If the 2 sides are occupied, nothing can happen. If it's 0, 1, it can go to 1, 0 with probability Q. If it's 1, 0, it can go to 0, 1 with probability P. And you remember from the first lecture that diagonal terms have to be the opposite so that the sum of a column is 0. So this is the local update operator of a single bond, okay, in my exclusion process. And if I really want to write the full Markov matrix, okay, there will be some boundary terms which I don't want to write because I did there are different types of boundaries. Boundary terms plus sum over i's, mi plus 1. For the very, very mathematical-minded ones, what I mean by this operator is the tensor product of the identity on the first side, identity on the second side, identity on the I minus 1 side, times this operator, times the identity on the rest, I plus 2, n, or L. Okay? And I have to add these local operators to construct my big Markov matrix of my system, which is 2 to the power L by 2 to the power L, plus boundary terms that I'm not adding. I don't want to get into that now. Is it okay? Yeah? Sorry? Oh, sorry, of course, minus p, yeah, of course. Thank you, yeah, of course. Thank you. Thank you. So now the thing is that in fact this matrix, you can write it in terms of Pauli matrices. So I remind you what are the Pauli matrices. So we are jumping from here to quantum mechanics. So what is the Pauli matrix X? I put the X up. It's just a matrix for a spin, huh? So I have spins. It's the good old matrix 0, 1, 1, 0. The Pauli matrix Y is with i's, which is not the same I, sorry. This is a site index, and the other one is square root of minus 1. The minus 1 is here. Yeah. Here this is square root of minus 1. And SZ is, so I chose 1 minus 1 or minus 1, 1? 1 minus 1. These are the basic objects in quantum mechanics for spins. And you can check. So I leave it as a little exercise. It's not very, it's just slightly tedious, but not very difficult. Okay, I can also define the lowering and raising operators, which are this one. So this is SIX plus, sorry for all the i's, they don't mean all the same thing, of course. One is square root of minus 1, and the other one is a site operator. And this is a lowering operator. Okay, now I have everything. So the mapping is the following. So this is AZAP. This is spin. So if I have an empty site, I call it a down spin with minus 1 here. If I have a full site, I call it an up spin. And my local operator, so here I have my local Markov matrix, which I just wrote there, where here I define a local Hamiltonian which couples two neighboring sites, spins, on the spin side, like that. Okay, there is an SZ term. And there are some slightly annoying boundary, first order terms, but which are not so important. Now if you, so this is, a priori this has nothing to do, this is another problem from quantum mechanics, if you want, times identity. not exactly quantum mechanics, but if I write this Hamiltonian in the basis up, down, 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 up, down, and up, I'm not going to write it again, you get the same matrix. You get essentially Q minus P surrounded by zeros. So it's the same one. It's a mapping. There's no approximation, it's clean. So it's not exactly quantum mechanics because it's not hermetic, yeah? But in the case of symmetric exclusion process, where only the boundaries, which I didn't write, break the detailed balance, P equal to Q equal to 1, this term goes away. This is a trivial term of identity, and you get exactly Heisenberg Hamiltonian of the XXX spin chain. P equal to Q equal to 1, H.
Not 1/2?
1/2. Yeah, you get 1/2 of Heisenberg Hamiltonian. You get one, you're fast. S.
No, they mean that P plus Q has to be equal to 1.
Oh, okay, otherwise I put a 1 and it's there's a 1/2. Yeah, you're right. I mean, if I take 1/2, I will have a global scale. It's not really important. So you get exactly Heisenberg Hamiltonian, the so-called XXX spin chain. But again, I mean, if P is different from Q, it's not exactly true. You have to twist the things a bit, and it's non-Hermitian here. But you know, you don't really care about. So what would be the? Of course, what would be the quantum mechanics evolution? It will be deep psi dt. I deep psi dt is plus or minus h psi, and we are interested in dp dt. Rather, is equal to mp. So we have no I, we are in imaginary time, and h and m, well, in fact, they are mapped to each other, so they are the same. So if we know how to diagonalize quantum mechanically over Hamiltonian, instead of having of sum of exponential of it times the energies, we'll have exponential time eigenvalues. Okay? So at least formally, if we know how to diagonalize the quantum mechanical Hamiltonian, we know how to solve the time-dependent Markov process. Okay? So here comes the miracle. Hans Bethe, in 1931, invented a technique to solve the XXX model. So this is Hans Bethe, invented the so-called Bethe-Ansatz to solve, at least he opened a huge Pandora box, which became a subfield, the subfield of integrable systems of mathematical physics, and he invented the Bethe-Ansatz to get the spectrum. So it's not the end of the story, because we are not asking the same questions exactly as in quantum mechanics. The Hamiltonian is non-Hermitian, so the eigenvalues will not be real. There will be different things, but at least we have a hold on the problem. We can use these techniques. So don't worry, I'm not going to give a full lecture on Bethe-Ansatz, although this would be the easiest for me, because this is really what I've been working on for the last 10, 15 years. This is my why I'm paid for, so okay. But no, I will not annoy you with that. But this is, of course, a very important method which allows to get very precise and exact results, but only for some very, very specific models. And we are lucky enough to have the fact that the exclusion process falls into that Bethe-Ansatz techniques, although the fact that we have open boundaries make it infinitely difficult. And the Bethe-Ansatz, in fact, for the system with open boundaries, has not been fully understood yet. There are papers even in the last few months, and it's not completely done. This is called, for the aficionados, this is XXZ spin chain with non-diagonal open boundaries, and this has been not solved fully. but people believe it's solvable. Okay, so now, so the idea is that the exclusion process can be analyzed. This is a message. I'm not going to tell you how, but what I'm going to tell you today and the next time is about some results using quantum integrability. So I'm not going to show you the cooking, but only show you the final dish using quantum integrability. Although these things are really quite beautiful indeed. Okay. And this is also used in many other contexts. Before I finish today, I would like to tell you some other mappings which are more physical. This was more kind of mathematical, very useful mapping to interface models and to the Kardar-Parisi-Zhang equation. Why solutions of the exclusion process tell us things about KPZ, Kardar-Parisi-Zhang. By the way, the fact that AZ can be mapped to quantum spin chains or can be integrated was first understood by Deepak Dar in the late 80s, but he never wrote it down. He just wrote a 4-line abstract that everybody cites in a journal that has disappeared since then. But anyway, but it was really, really studied, and the first seminal paper after Deepak's seminal paper was a paper by Gua and Herbert Spohn, who really studied the upper part of the spectrum by better ansatz, found a gap, and so on. I don't remember the year exactly, it's 90 plus, 91, 92. And this opened the way of the quantum integrability studies of these non-equilibrium processes.
So this is the solution with quantum integrability is a more recent development, right? Because before there were solutions to the model that didn't use that.
No, I would say, so I will go more into details, but it depends on boundary values. There has been a very important paper by Derrida, Evans, Pasquier, and Hakim and Pasquier, who used another technique, which is a kind of matrix ansatz, but which in fact is deeply related to algebraic better ansatz. Okay? Almost simultaneously, but on a different context, more the gap and so on, Gua and Spohn used the traditional coordinate better ansatz. And if you heard about it, there are some very important contemporary, the last years and still now, developments in the pure mathematical side of probabilities. It's the so-called integrable probability techniques, where you solve probability systems using integrability. It has become a subfield of probability. And some key names are Sasamoto, Corwin, Borodin, and they built, so it's also related to better ansatz, and they built on previous works by Tracy and Widom, and we are going to talk about Tracy Widom quite a lot, about KPZ. It's a whole field, and they have plenty of students, and you probably, some of these names are familiar, and this is a very powerful method. So it started from a small seed, but it's really opened a lot. So I want to tell you the relation with KPZ, because this is pretty neat and pretty nice. So you can map the exclusion process to an interface model. So exclusion process is an interface model. And the mapping is again quite elementary, and it opens another interface model. Another point of view on things, so I just have to be careful to make it clean. It's not so easy to draw on the blackboard, but suppose I'm looking in the bulk. Don't worry, boundary condition can be taken into account, but it takes more time, and the bulk thing is really important. So what is the exclusion process? It's a configuration of particles and holes. So I put particles somewhere. And of course I will not have enough space to draw what I wanted to draw. Okay, and the idea is that instead of representing this as particles and holes, you draw an interface. When you have nothing, an empty site, you draw a line at 45 degrees, and when you have an occupied site, you draw a line at minus 45 degrees. So I can represent my configuration of my exclusion process as a line, as a broken line, and one has to be careful to draw the line in between. So for example, this will go up, this will go up, this will go up, and of course I'm probably wrong, this will go down, this will go up, this will go down. You see, I'm already shifted, but you'll do it cleanly on your own paper, and this will go. Yeah, it's a mess. Sorry for that. Something like that, okay? Each time I have a hole, I go up. Each time a particle, I go down. I probably messed it up, but I should. Okay, three ups, one down, one up, two downs. And it's not really on scale, and two ups, okay? When a particle jumps to the right with rate p, what happens to my interface? Well, it will change a bit, and this last thing will look like that. The rest will not be changed. So it's as if I have deposited a block with probability p. Okay? If a particle jumps backward with probability q, it's as if this part had evaporated with probability q. So it's a Tetrix game. Okay? Tetrix. And now, instead of hopping of particles, I have an interface on which I'm depositing or evaporating bricks. And the interface moves. So you can analyze this system. And this is a so-called a solid-on-solid model. And another very popular mapping, another very popular way of seeing these SOS models are the following. You just have to change a bit the angles. So you have stacks of bricks. And so on. And you have bricks which are falling from above. And you suppose that your bricks, there are cubes which are made of this Velcro, the things you use to close your shoes. Yeah? So whenever a brick falls, it's going to fall in these tubes. This brick will fall and will stop here. It will be pinned. Okay, so I have these bricks. So some holes remain. Okay, for example, if I have something like that, a tower here, and a brick which is following, it will just stop here. So this is called a solid-on-solid model. Okay. Sorry for the pictures, which are not very nice, but okay. And the idea is the following, is that this whole class of models, there's a universal equation, which somehow, so if you do this on your computer and you simulate it, in the end, of course, you will not see the structure of the bricks anymore. You will see an interface which is growing. Another way of obtaining such an interface is by a negative. You take a piece of paper and you try to burn it carefully. Then the burned part will advance and you will have an interface of burned paper and normal paper. And there is a universal equation to represent such interfaces, which was written by Kardar-Parisi and Zhang in 1986. That's a real seminal paper, and what they want to represent is, it could be in higher dimension. I just draw things in one dimension because the mapping is true in one dimension. But I have a height over a substrate. The substrate could be a plane, and I could have a heap over it. And the equation is the following. The time variation of this height function is nu nabla square h plus, these are just conventional coefficients. So this is supposed to be a Gaussian white noise. I will explain each term in a second. 2D. So it's space-time white noise. So this is how the height changes with time. This is a diffusion term. I mean, sometimes when you deposit a piece of sand, it will roll down a bit. This is the important term, in fact. This tells you that when you deposit something, the sand will stick here, and the growth will be towards the normal of the surface. So this is very important. If you take lambda equal to 0, you fall into a different class, which is called the Edwards-Wilkinson class. But for KPZ, this idea of sticking Velcro cubes or this mapping is very important because you're growing in the normal direction. And this is the noise which represents random deposition and evaporation of material, if it's sand or snow or whatever, on your heap. So this equation, of course, was very, very much studied. You have to specify the initial condition at t equal to 0, as usual. And it acquired a mathematical status only very recently through the works of Martin Herrer. Martin Herrer is a mathematician who got the Field medals for developing a whole theory of stochastic, partial differential stochastic equations and processes, rough paths. Among them, KPZ is one of the most prominent examples. Yeah?
What is the D in the second term?
This here?
No, above.
Here?
Yeah.
Gradient?
No, the D.
Oh, it's a coefficient. It's a coefficient. But it's just a conventional coefficient. It's a name of, yeah. In fact, it's a good question. Lambda, if I think about exclusion process, it's related to P minus Q. So in the symmetric case, lambda vanishes.
KPZ is sometimes compared to Burger equation, like a
Yeah.
diffusive advection.
Yeah.
So diffusion is clear, but why the second term is related to an advection
Yeah.
term?
In fact, if you remember Burgers, it's ddx of u square. Yeah. This is Burgers, u dx du. In fact, the mapping from this to Burgers, if you define rho, no, u, because I call it u here, u is equal to gradient h. Take one more gradient of this equation, call u is equal to gradient h, you will end up with Burgers. Okay? With some noise. So in fact, this is this term, this one.
And the gradient of the noise. I should think about the gradient.
And it will be with conservative noise. So it was studied before by David Nelson, Foster, and I forgot the third name. And there was a paper even earlier than KPZ in which they were studying the noisy Burger equation, which is in fact equivalent to it, up to a gradient. So, do I still have a few more minutes? Or yeah, maybe 5 minutes to finish this presentation of the exclusion process and some mappings. I want to tell you about two other very nice mappings, and then I will stop. So first of all, let's take a special case of that. We'll take a mapping in the case we have an infinite system with initial conditions where all the particles are on the left and holes on the right, and then we let the thing evolve. Well, if you draw the interface, it's very easy. It's just a corner. You go down, 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 and you go up by the same rule as before. Okay? Now if I let my particles hop, the corner will deform. And if I, for example, after some time, the new configuration would be something like that. I don't know, like that. But if you draw it Of course, I'm going to draw it in a very bad way, but on your paper you will do it in a finer way. Up. So this is empty, 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 empty. And okay, it's a disaster, of course. Anyway, it will become something like that. Okay, so my corner will deform. You'll do the right picture. What will happen is that I can tell you the answer. There will be a strip here, and the length of the strip will be the distance made by the first particle. There will be a second strip here, and the length will be the distance covered by the second particle, and so on. And those who have not moved, they remain like that. Do you follow me more or less? It's not so easy to draw on the blackboard, especially when you're height challenged. But anyway, okay. Especially if it's a height model. Well, this is very difficult. Okay. Anyway, so if you turn your head or you make 45 degrees, what you're building is a dynamically growing Young tableau. Young tableau. A Young tableau is something we use in quantum mechanics to encode for permutation symmetries, symmetric group. At least probably you heard the name. So the Young tableau, they are very much related to permutations of objects, permutation group. So in fact we are doing something on the permutation group, Sn. S infinity in fact. Okay. Anyway, there's another problem which is extremely nice, which a priori has nothing to do, but which is totally related, is the Ulam problem. So I take numbers, let's say I take 7 numbers, 1, 2, 3, 4, 5, 7, and I take, I don't know, 2, 5, 1, 3, 7, 4, and 6. So it's a permutation of 7 numbers. Okay? So it's a permutation, sigma. And I can ask the following question that Ulam asked. Can we extract some growing subsequence? For example, 1, 3, 4, 6 is a growing subsequence that I extracted from my 7 digits. Okay? Another one would be 2, 5, 7. It's a smaller one. Okay? There could be other ones, but we are interested in L of sigma, which is the length of the largest, there could be degeneracies, growing subsequence. Looks like a very academic problem, but it's not. It's a very fundamental sorting problem. You know, sorting in computer science is important. So if I give you 100 numbers, but they are of course intermingled, they are, and I want to find in these 100 numbers a growing subsequence. Well, in fact, and suppose now that I choose sigma, the permutation, with probability 1 over factorial n. I take any 1 over factorial 7 here. Of course, if I take 1, 2, 3, 4, 5, 6, 7, it's ordered already. If I take the opposite one, it's very bad. Only one, the length is 1. So I can ask myself, what is the statistics of the length of the largest increasing subsequence in this random process where I choose a permutation and I look at the largest one. So what is the statistics of L? Well, one can show, this is a classic work, in fact, of the 50s, I think, that the statistics of L is related to the statistics of this Young tableau. And in fact, of the first line of this Young tableau. And this Young tableau is related to an interface problem, which is itself related to the exclusion process. So in fact, the answer to all of these questions. What is the shape of the interface? What is the height of the interface, for example? You can look at the height here of the interface. What is the statistics of the height in KPZ? What is the current in the exclusion process? What is the statistics of the length of the largest increasing subsequence in the random permutation of numbers? They are all related, and they are all related to properties of random matrices, and I'm going to end now. We are going to talk about that next session. So they are all related, all identical problems, or mappable, or isomorphic problems, if you want. Problems, especially the KPZ one, or the statistics of the current. Yeah, something very important I didn't say. If you do the drawings many times, you will see that the height over the apex here is exactly the total number of particles that jumped through this bond. So it's the current statistics. So the height statistics and the current statistics in the exclusion process are the same. Height statistics in KPZ and current, which is non-equilibrium, which is our initial interest, statistics in AZEP, they're just related. Okay? And all the other problems are here. So all isomorphic problems can be understood. Any progress in one of these problems entails a progress in the other ones. You can map things by using properties of random matrix. And we are going to talk about that next week, on Tuesday. Okay, thank you very much. Sorry for being a bit long.